My name is Harald Wendel, working for TransferWise, and I'm going to talk a bit today about microservices, how to make them transactional, and actually going to present you a pattern that you can modify or use as is if you want to build a transactional architecture. So first, a little bit about myself. I'm an engineer at TransferWise. I'm with the company for a little bit more than 3 years. Actually, the company doesn't exist only for, I think, 6 or 7 years. 15 years of Java, started somewhere at Java 1.3. Before joining TransferWise, I was working for Deutsche Bank and essentially spent like the last 10 years building all kinds of trading and risk management system. And now I moved a little bit more into the fintech space. Cool. So what are we going to talk about today? Essentially, how to build a transactional microservice architecture that scales. And a little bit, just some recap on transactions and Kafka, because that's what we're using. The background here is that at TransferWise, we are currently running, I don't know the exact number, but it's something like 50 plus services, and it's constantly growing. Since we are a payment, well, how to call it, a payment processor or payment provider, it's essentially quite important not to lose any data. And like if a customer, for example, comes to our website or comes to our mobile app and wants to send money, then in this process there are already like at least 5 or 6 microservices involved. Obviously, again, we can't afford to lose any data. Like we're doing a fraud check and we're doing an email checks, and then we convert the money and all the kind of things. They're all in different services. And the data needs to travel between those services and doesn't need to be lost, and also needs to scale. So because like we have quite a lot of customers, and the traffic is actually quite high on the site. Why should you listen to this? So the problem where we are coming from, and I think that's quite a typical problem. So if you have a startup or you have a new project or a new product, and essentially, what you usually do is like you have the single service where you put all your logic in there, and then you become successful, and just suddenly this doesn't work anymore. Like there are more users, there's more load, and suddenly small performance gaps, they become quite big, and then your service just dies. And that's usually the moment when most of the people start thinking about modularization, but actually you should do it a bit earlier. So yeah, this is actually what happened at TransferWise to some extent. You should listen to this if you're just interested in building asynchronous systems. And then the talk before on Java 11 mentioned a couple of those reactive patterns. And actually what we are building here is kind of a transactional reactive system. Like so services, they are essentially publishing changes out, and our services can listen to them and react on them and modify state. So this one. And if you just want to hear what we're doing with Kafka, because it's not a traditional use case for Kafka, but it works very well. So yes, it's actually an interesting new angle to it. So this is the structure of the talk. So we're going to quickly do a quick 5 minutes recap just on transactions, what they are, so that you're all on the same page. Then I'm going to show you what kind of problem we are going to solve. And this essentially is a real problem we had at TransferWise. So it's pseudocode, but it roughly resembles what we were facing. Quick recap on Kafka. Main reason for this is just to show you how it's built internally and why it's able to scale. Our solution, so how we are using this and how we are applying all of this and build this architecture. I'll show you some performance stats and graphs, and we'll quickly run through some alternatives. And then if any of you has some questions, we can do a Q&A. Great. Let's start on transactions. So, what's a transaction in computer science? It's essentially an atomic unit of work, which must either complete entirely or not at all. So usually there are multiple steps involved, and if it doesn't complete, then those partial steps need to roll back, and from the outside it would look like as if nothing happened. So a transaction moves the system from one valid state to another. So essentially, I mean, you all know it. Like if you modify a couple of tables in one transaction, so to assure, so the state afterwards, this transaction completes, is a valid state. So you don't have the situation where only one table of the three you want to modify is actually modified. And a transaction can be distributed or local. So, I mean, mostly we are using local transactions, but like a transaction can also be distributed across several services and network hops. And I'm going to talk a little bit more in detail about this one because it's good to understand what you're trying to solve here. Yeah, and obviously a transaction must adhere to the famous asset properties, which are like atomicity, consistency, isolation, and durability. So let's just quickly run through what this is, just remember it. So again, like transactions either complete entirely or not at all, and if one part fails, then the whole transaction fails. Actually, quite straightforward. Consistency, yeah, transactions move a system from one valid state to another, and this is also very interesting. Like later on in the context of this talk, like what this actually means. Like what is a valid state? Is it just like if you look at some code I've seen, you usually have a controller or REST controller, which is then annotated with @transactional, and it does something, but maybe you can break it down a little bit more into smaller pieces. We're going to talk about this later. Yeah, isolation. Essentially, think about this as a lock in or a synchronized block in Java or as a mutex. So some of the transactions can run in parallel, like if they modify different pieces of the system, like different tables or different rows, but some of them can't, like if they are modifying the same role, like and for example, like MySQL and MariaDB, they use some row level locking. So essentially, parts of the transactions are serialized, and parts of the transactions are not. Yeah, and the durability changes are essentially stored permanently, and on the durability piece in our architectures, actually, it's more like eventually durable, but I'll come to this later. Yeah, as I said, distributed transactions. So usually they involve multiple network hosts, like a database and a GMS broker. And common implementations use a two-phase commit to guarantee those asset properties. In order to, so a two-phase commit essentially works in a way that you're going to all your hosts and all your services and asking them to actually advance the transaction until the very last moment. So essentially, they're doing all the checks, and at the last moment, a transaction manager then sends each of those services a message and says either commit or abort. So transactions are rolled forward to the very last moment. Then they report back either I can commit or I can't commit. And if all report back okay, then the transaction coordinator tells them to commit actually. Yeah, and that's one of the problems with distributed transactions, that you essentially need this transaction coordinator. Yeah, and in Java, yeah, we have the JDA API, which you can use to implement transactional resources. So again, the common ones we know is like a database and message broker, but you could go and implement the transactional file system or transactional memory or whatever you can think of. And usually EGB containers, they have it out of the box. But if you just run like the standard like Spring Spring Boot and whatever, like single microservices, then you will have to use some kind of standalone transaction manager, and there are a couple of them out there, like Atomicos and Bitronix, and I'm quite sure there are a couple more of them. Cool. Yeah. So now we know. Now we just got a bit of a lesson about transactions, just to remember our school days. Now, what problem are we trying to actually solve? So yeah, that's what we had at TransferWise, like a monolithical application like Grails, 500,000 lines of code. And obviously at some point this didn't work anymore. Like all kinds of functionality in there, and like some admin functionality could essentially break some customer-facing functionality and so on. So this is not good. And essentially, so just a standard monolith, like a monolithical thing, like in our world, it's a payment processor. You can put in whatever you want here. So it's like you have the service, or maybe it's even a controller. So what people doing is they annotate their service method with a transactional, or we can locally start a transaction like manually, but that's what you usually do, and you do when you're using Spring. And yeah, it does two things. It does pay out to a recipient and notify a customer. And obviously, what you want to achieve here is essentially we either want those both things to happen, or none of them. So you don't want to pay out and then not notify the customer, and you don't want to not pay out and notify the customer. So this is not cool. And yeah, now if we move to a microservice world, this changes a bit. So what we are trying essentially to do now is like moving from monolith to microservices. We want to split off some of the functionality, like we're introducing like an email service with a separate database, for example. And then this code now looks something like this. So this is what people usually implement. And the reason why they do it is that I very often see those transactional annotations being at a very high level, again, at a controller method. And then inside you call like, I don't know, millions, billions of services. And then somewhere someone changes like from saving the email message locally to just calling a REST service. But now this is no longer transactional, right? Because now this is not a transactional resource. So you just like you do the payout, and then you notify your email service, telling like, yeah, please send the customer a message. And now, like, if something happens here, like let's say after email client notify the customer, and like say the database dies, right? Then this transaction essentially will be rolled back. So the payment will be never processed, but you already told the email service, please send a message. So we are ending up exactly in this situation. I talked to you before that we did some of the parts. So it's no longer atomic essentially. We send out. We completed one part of the atomic unit of work, but not all of them. So yeah, and this is actually just what I saw. Like something happens, something dies, then the transaction manager, we can listen to the rollback method, but we can't unnotify the customer anymore. It's already out there. So yeah, that's not so good. Good. What you could do is like, and this is actually quite a traditional approach, and I think it has been done millions of times. Use this GTA transaction manager, as I told you before what is this, and yeah, essentially just send a message to a GMS broker, new customer notification, and the message will appear only on the GMS broker if the transaction completed successfully, and if it's not, then it won't be there. And then you essentially have like a picture like this one. So we're having a transaction between the payment processor and the GMS broker. And then again, we have a transaction between the email service and the GMS broker as well. And so this is how it flows through the system. And then you can see this transaction manager. So if this is not an EGB environment, you can see this transaction manager, which just sits there, needs to be connected to everything, becomes a single point of failure, and so on. And yeah, this is not really, this didn't work for us. And the reason why it didn't work for us, first of all, is throughput. So we were using So we actually tried to use a JMS broker, and since we are a small company, we obviously didn't want to buy into some TIBCO infrastructure or something else that's highly paid. So we were using the Artemis message broker, which is essentially, I think, a fork of the active MQ of the active MQ project. And the main problem with this one was that throughput. So like what we managed to do was 70 messages per second at a maximum. And since the company is growing like 60-70% per year, and as is our volume and as is our user base, so like a couple months later, this already didn't scale anymore, and we had to think about ways of getting rid of it, and figure out something that's a little bit more scalable. And so we started to look into Kafka, and Kafka has quite a good reputation about being persistent. So it's persistent messaging, and it scales. Like if you look at what LinkedIn is doing with it, so I think they are pushing billions of messages per day through it, which is quite impressive. And so we thought, like, yeah, let's have a look. But obviously, the drawback of Kafka is it's not transactional. You can't participate in a GTA transaction. So we had to figure something out, and I'm going to show you a bit later what we did. At this point, let's just do a quick recap on Kafka. I just want to quickly talk through how it is working internally, why it is different, and why it actually scales. So why Kafka? Yeah, I already said it. It's highly available. So Kafka is usually deployed as a cluster. You do at least 3 nodes. We are running 5. It has high throughput. So I think currently we are doing like peak 5K messages per second, but that's not nearly close to what it can do. And it is eventually persistent, meaning in this case that at some point your changes will be on the disk, persisted to the hard disk, but for some time they will stay in memory. It's not a problem for us because we are using a cluster, and obviously if you use a cluster, you send your message to a couple of nodes, and this way you are protected against the failure of X amount of nodes depending on your cluster settings. And this is essentially what Kafka looks like. So the idea of Kafka is it's a append-only log. So it's like a long, think of it like a long array where you just append new messages at the end of this array, and then consumers essentially start reading from the left side, and writes go from the right side. And this log is actually partitioned, or it can be partitioned. So the standard is 1 partition, but you would use multiple partitions depending on your setup of your microservice. So say if you're running 2 nodes, you might want to use 2 partitions because you want to process it in parallel on both of your nodes. And what you also can do, you can also assign, if you send a message to Kafka, you can assign a key, which essentially determines onto which partition it goes. So if you have strong ordering requirements, like for us, this is a customer transfer, which involves multiple messages, and we want to ensure that it always goes in the same partition, so we set the transfer ID as a partition key. And this solves this problem. Yeah, and as I said, like the main difference now between what the JMS broker is doing and what Kafka is doing. So a JMS broker essentially is holding the queue, the message queue in memory on the program, and then is pushing out the messages onto the client. And obviously the problem here is like that if there's a slow client which can't process the whole queue, the memory of this the used memory of this broker just grows, and essentially what happens is you're going to run into out of memory and your broker dies. And this can't happen with Kafka. That's the cool thing, because the way it works is like, again, you have this log, you append it, and then all what the consumer does is, so there's no broker that pushes the message. there's essentially a consumer who keeps an offset in this log and just advances as fast as he can. And now you don't need any back pressure or stuff like this anymore. You can just like go and consume the messages you want as fast or as slow as you want. And we usually, so messages in Kafka have a thing called retention, essentially meaning they stay there for an X amount of time. So in our case, it's like 1 week, which is pretty enough which is enough to be sure that we don't lose anything. But you can also like put it to a year or whatever you want. And let me just go back. And what the consumer does is, since we have no broker, we have a broker, but the broker isn't pushing anything. The consumer is essentially pulling this log. So there's a constant loop. So you usually spin up a thread, then have a pull looper, and it's just taking new messages in from Kafka instead of having the broker push it to him. Yeah, and that's essentially what a cluster looks like. So you have several nodes. Each of the partitions of a topic has a primary node, and then it's replicated to the other nodes in the cluster. In terms of like subscribing to a Kafka topic, you have like queue and topic semantics at the same time. So Kafka knows something like a consumer group, and within a consumer group, strict queue semantics apply, meaning that only one consumer can consume a given message. While if you have multiple consumer groups, you can have multiple listeners to multiple consumers of the same topic. Good. Yeah, Kafka design notes. So Kafka is at least once delivery, and lately there has been a new version of Kafka, like it's like Kafka 1 Plus, which provides exactly once delivery. To be honest, we haven't tried this. We haven't figured it properly out yet how it works. But essentially, it's more like it's not really applicable in our case. It's more like on the stream processing use case for Kafka, where you essentially listen to a topic, do something, and then push it out on the next topic again. And there you can have this exactly once delivery semantics. Yeah, and I told you before that Kafka is eventually persistent. So, and the way it works is, it doesn't use a lot of memory. It uses the page cache. And if you know Linux, you know that essentially Linux uses all the free memory it has to load file system pages. And what Kafka does essentially, just like it gets a message, it writes it to a file, but it doesn't do an fsync. So it doesn't tell the file system to actually sync it back. So what this means is that essentially the data can remain in memory for some point until Linux and the operating system decides by itself to actually write it off to the disk. But this is what it makes fast, because it's essentially just a writing to memory. And since we saw that the Kafka partition is essentially like this array, you can use linear reads and writes for high throughput, because it doesn't have to do fseeks and doesn't have to do random access on the file system. It just can essentially just like push it out and read it from there again, and it can keep things, whole cache lines and things in memory, which is yeah. I mean, I've been working with messaging systems for quite some time, and the speed for a persistent messaging system is really impressive. And this is just like what our cluster looks like. So we are running on 5 nodes for virtual CPUs, actually virtual hardware, for virtual CPUs, 16 gig of memory, 500G SSD, and currently 1 gigabit NIC. But we're moving to 10G here. And ISR and replication factor is interesting. So replication factor means on how many nodes is your message replicated, and the ISR means, which is called the in-sync replica set. That's essentially if you publish a message to Kafka, this means how many nodes need to respond with an ACK telling you that it has been it has been actually stored on that node. And then the master node in the background will also replicate it to the other nodes. And usually what you have to do is you have to choose an ISR, which is replication factor divided by 2 plus 1. Yeah, as I said, it runs on virtualized hardware. And we are using 3 zookeepers. So Kafka doesn't do all the stuff like leader election and the master essentially selecting the leader for a topic and those kind of things by itself. But it just uses zookeeper for it, which actually works nicely and actually quite, in my view, is quite a smart design decision not to try to write it again. Good. Let's jump onto our solution. So what we're doing is essentially, since we don't want to use GTA, we want to use local database transactions because they are fast, like a transaction on a MySQL database, which is co-located or whatever, is quite a fast thing. So if we go back to this long and annotated controller or transactional controller method, which does who knows what. We decided what you can do is, or what we did is essentially split those things into small pieces, and each of those pieces essentially can be executed locally using a local transaction. And then what happens is, so once this transaction is completed, it essentially stores the fact that this transaction has been completed together with a unique ID, which uniquely identifies the transaction that just happened in the system, and then essentially forwards this as a notification to the next service. So it's a kind of a classical store and forward thing. And yeah, to store the notification, as I said, we use the Kafka broker. Yeah, use Kafka for higher throughput, and the way we're doing it. So this transactional code actually doesn't send the message out. What it does is it just stores the message in a database table. So we have the transaction, as you can see here. We do a couple of inserts, we do a couple of updates, deletes, and at the end we essentially want to store the fact that this has been completed and that the customer now needs to receive a message. So we just store this into a table, do commit, and we're done. And we don't have to think about it anymore. And we can just continue with the next to serve the next HTTP request. So this is now what it looks. So you're back to got rid of the GTA annotation. We don't have this call to the email client anymore. It's just a nice and local and fast database transaction. So now, what does a message look like in our world? So essentially, like, so we have this abstract class message. Can be interface or whatever. Key here is this UUID, because this UUID is later on used for deduplication on the consumer side. Because I told you before, Kafka has at least one semantics, which means that a message can arrive multiple times on the consumer, and you need to do something in order to filter out the duplicates. And it has a destination, which essentially is a topic. And then, yeah, you do a customer notification. You put in your payload you want to send, your fields, and the destination. And then this whole thing is essentially. And so what we do, we just serialize this message as a payload, as a text field, and have the destination. That's what our message table looks like. Just a destination and a payload. And it also has a primary key and ID, but that's not so important in this context. Cool. So now what we're doing is polling, and now some of you say, "Oh, polling is not cool," and especially polling a database. We actually already did an improvement to this. We are using a post commit hooks to speed it up even more, but polling is actually fine for us. So we have a separate component, which can be a separate process, which can be just an in process, like built into your microservice, just a Spring service, which just essentially does what? It selects a bunch of messages from this message table, sends them to Kafka, deletes those messages. once it gets a successful arc. So, and with this, essentially, the fact that we completed this transaction, and especially this piece of code is now published forward. It's persisted, so it adheres to all the asset properties, and yeah, we can just delete it from here, and that's what's actually keeping this message table quite small and fast. So this is what it looks like. Like we have a message sender. It's a thread. It's running, pulling from the database, sending to Kafka. So this is what send to Kafka looks like. So we're using the asynchronous send because yeah, we want throughput, as I said before. So we're sending it out to Kafka, waiting asynchronously for the callback. When we get the callback, we are removing it from the database. And you can already see here, again, why I'm talking so much about at least one semantics, because this essentially what essentially can happen here is that you're sending a message twice. If you don't get an ACK for some reason, or if you have a network failure or whatsoever. But now if you keep in mind that we have this unique ID which identifies this message uniquely across the whole system, you can think that you can see where we are going with this and why it's actually not a problem. So how does the consumer side look? So essentially, reading from Kafka, setting up a pull loop, and then you again start your local database transaction. And what this transaction does is it does a duplicate check on this unique ID, and again does just whatever it needs to do, like running business logic, inserts, updates, and commits in the end. So this is what our message processor looks like. So it's just it's just a thread. It's pulling messages from the consumer from the Kafka broker, processing messages, and does an async commit. So, and this is actually the implementation of the in-process message processor. Like, and this is now again transactional, and you just move your state from one service to another. It's fully consistent. You didn't lose any data, and now what you're doing is duplicate check, and yeah, you essentially try to so we use a database again for this, but it doesn't need to be MySQL, can be whatever. I've seen a lot of implementations using Redis or whatsoever, but essentially you're checking whether you already seen this message, and if not, then you're continuing doing your local database transaction. And yeah, that's the picture we are ending up with in our world, like payment processor, local DB, email service, local DB, and Kafka. And actually, what the cool thing, so there's actually two more things which are really cool about this kind of pattern. So first of all, it's the email service doesn't need to be up and running. So you can still process in your payment processor. You can still complete your local database transaction. You can push your state further, and essentially Kafka acts as a state buffer. And you suddenly don't have those. So if you think about just like a microservice architecture, we are doing REST calls. So we are calling directly other services from each other, and we all know that the availabilities of those services then multiply. This can't happen here. So if email service is down, fine. Well, it's not fine, but we can bring it out later on, and then it can still continue to process the message. And the second cool thing is that actually the payment processor doesn't directly modify the state of the email service. So instead of the email, this is a typical reactive pattern. You just listen to a message or to an event, you react to it, and you're doing something, but it's still transactional. Good. Let's talk a bit about performance, because what we've seen before is it's all a bit. So we're doing polling from the database. We're doing duplicate checks and all kind of things, and they might seem slow, but they're actually not. At least with in our workloads. So first of all, which components do we have and which components are we monitoring? So we have a message loader, essentially a process that loads, it pulls the database, loads those messages into memory. Then we have the message sender, which takes those message batches and just pushes them out to Kafka. And we have the message consumer, which needs to do the deduplication, pull from Kafka, and then obviously we are also interested in end-to-end performance. So this is what we have, and this data is about, I'd say, 3-4 months old. I think it changed quite a lot since then because again we are growing quite a bit. But in our system, so we're setting a max batch size that we load from the database of 500. But the average batch size is 20. So on average, in every pull from the database, we only have to fetch 20 messages, which is super fast. And the way it works, we have this. I showed it before. We have this thread running, and if there are no more new messages, we just sleep for 500 milliseconds and then try it again. And obviously, now we have 500 millisecond latencies, 500 milliseconds of latency in the worst case. But in our case, it's not really a problem. We don't have those absolutely low latency requirements, so we're still fine with latencies. Let's say if it's below 1 second between services, I think it's very good for us. It actually is. What we are interested in is actually throughput, like a lot of messages to go through the system. Yeah, and actually, on average, it takes about 90 milliseconds to get a whole batch of up to 500 messages into memory. And what we're using here, at least for the service I'm describing here, is MySQL 5.7, but we're also running this on Postgres and on MariaDB. Good. Yeah, and this is essentially the distribution in our system between batch sizes and the counts of them. So like most they are in the up to 50 messages, and then the large ones are very seldom. Yeah, and this is essentially the latency, and you can see that that latency actually doesn't depend that much on the batch size. So of up to 100 messages of up to 100 messages in a batch, it takes like 50 milliseconds to load those into memory. And again, this is why you can optimize the polling by using it. Because what you can do is like when you do a local database transaction, you can register a post commit hook, which then immediately triggers actually the sending out of this message. But this is really only required if you really need low latency. So for us, this setup actually works fine. Yeah, and the message sent essentially that we're using here is like 4 publisher threads, and it can publish out 700 messages per second on a busy day. And this is just for this one component. So this is just what this one service does. This doesn't mean anything with regards to the performance of the whole cluster. So we can, as I said before, we've seen 4,000 or 5,000 messages per second on a cluster without any problems. Yeah. So and here we have essentially just the message sending thing again, count versus latency, and you can see that it takes an average like somewhere in the low double-digit milliseconds time to send out the actual message and get rid of it. So far we are for a batch, since we're using asynchronous publishing, it takes about like 100 milliseconds to get the batch from the database and push it out to Kafka and be done with it, which is good for us. Message consumer. So the usual setup is 1 thread per partition. And what we can do is, or what we see in our system is like 300 messages per second per partition processing. And the key and the main limiting factor, but besides actually the actual business logic, but this is something you can do locally differently, is the dedup time. So with MySQL, it takes about 3 milliseconds to do a duplicate check. If you need something faster, you can think about using a memory dedup check or whatever. But this is what we can achieve by using a database call. Again, in our case, it's enough, but yeah, if you need more, if you need better times, then you have to figure something out. Most likely something memory-based. Yeah, and fast deduplication is the key to high throughput. So end-to-end latency. So as I said before, we are caring actually more about the throughput than latency. And it's actually quite a common thing for a lot of those customer or internet platforms which have a lot of users. So usually throughput is more important than the latency. We're not like a trading platform which needs to go to the market or whatever, where we care about microseconds and milliseconds. So, and when we built it, we unfortunately made a mistake. We're storing timestamps only per second and not with millisecond precision. Something that we need to change. And but we have some recent data, and actually shows that a round trip, like a message from one service to another via Kafka, is about so essentially from the moment it gets loaded from the database, or from the moment that you save it in your local transaction to the database until the moment where you have it available in your other service is about 300 milliseconds. This is in the same data center where you have stuff like collocated. But yeah, that's the overhead of, obviously it's not in-memory messaging, it's not multicast or whatsoever. That's the overhead that we have, but for us it's really fully fine. Good. Yeah, so much about this. Let me quickly just run you through some alternatives. So yeah, we discussed it before. You can just use the JMS broker with transaction support. But most likely you will have to buy one, because at least we couldn't, for example, we couldn't even make Artemis run on 2 nodes. It just didn't work for us. I don't know why. Maybe because it's us and we're stupid, or yeah. ActiveMQ is, I think ActiveMQ is very similar. I think Artemis is the successor of ActiveMQ. So those are the well-known free available ones. Obviously, you can have TIBCO, and at Deutsche Bank we are running quite a lot of TIBCO servers, which have more throughput and which perform better. But still, I doubt that you can get in the regions of Kafka with them. So then, when I did research for this talk, I stumbled across something which is called JBoss REST AT. That's essentially a transactional REST calls. So that this pattern that I showed you before, that you have your local transaction, you have your distributed transaction, you do a payment, you process the payment, and then you call out to a client. This specification is supposed to do it in a transactional way. So again, using I suppose a standalone transaction manager, but at least it solves this kind of problem. So you you can already do direct REST calls from your transactional code, which is a step forward. When I looked it up, it was still a draft, and I think it's supported by the Wildfly container. I'm not sure what the latest state of this is. This was like 3 or 4 months ago. Yeah, and obviously you can write your own XA stuff. Like with the JTA API, you can essentially, as I said before, you can implement all kinds of transactional resources. You could essentially try to somehow fit this onto a REST-based architecture. Good. Yeah, and since this is actually just a pattern that I'm presenting, so you don't actually have to use all the technologies I described here. You don't have to use Kafka. You don't have to use a MySQL database. So you essentially can choose whatever you want. So you can choose, I don't know, if you say I'll try out RapidMQ because it's just easier for me to use. I'll check this one, or yeah, try a different database, try Redis or whatsoever. And what you can also do is, like, essentially in this pull loop. So this message sender component I showed you, which is actually pushing the messages out to Kafka. What you could do is you could just try and do direct REST calls from there, like essentially message which tells you which method or which endpoint to call, and then just do it from there, and you would have potentially similar semantics. Yeah, and again, add post commit hooks if you really need low sending latency. And we've done this. We have a couple of places where we are doing this. But yeah, so right now I don't think it's to me in most cases it seems to be like an overtuning of the system. Yeah, that's it. Thanks a lot. And if you have any questions.
So guys, if you have any questions, you just raise your hand and I will bring you the microphone. Any questions? I see. I'll start with the first row so that I don't use the ladder.
Sorry, maybe I not understand it totally. Can you recap once more? So how you keep your distributed transactions? So at first you store required action in the local database inside transactions, and then you have the consumer which go through them and execute them, yeah?
Yeah. Yeah, so again, like you store the outcome of your transaction locally in the database, as you just said, right? And then essentially by making sure that it's committed onto the Kafka broker, you essentially now know that the message is there, so it's forwarded. And then again, when you consume it on the other side, you can just retry it. Like if something fails, you can retry it, and you use the unique ID to filter out the duplicates. That's how you. And there's no place where this data can essentially disappear in this process. And that, yeah, essentially like replacing a whole large distributed transaction with a very small store and forward architecture. Do something, forward the result, consume it, do the next step in the whole process.
Hello. Thanks, Harald, for your experience. Can you please share how long it takes for your team to totally migrate for this new approach?
Oh, we are still on it. I mean, like what we have at TransferWise is like we have the monolith, and to be honest, the monolith is still at the same size. But at the same time, we've written like 1 million lines of code just in microservices. So what happens is we are growing. We are not growing the monolith at least anymore. It's slightly declining, and we're just writing all the services around it. But so there's no good answer to like how long it takes it for. It depends on what you have in your solution, what you have in your system. It's hard to answer. It really depends on your very setup. But just to jump onto it, what you need is like setting up a Kafka broker and then go from there and play with it. If that answers your question. No.
Yeah, probably I have another question. It's related to set up the Kafka cluster. Do you use any cloud solutions, or it's on-premise?
No. So, well, we are currently migrating onto AWS, and we're going to run it there. But now we are running it on-premise, essentially, on our own hardware.
Yes, hello. Thank you for your talk. I'm right here. I left, yeah. Yeah, okay. Here.
I can't see you.
Left.
Okay,
downstairs
sorry.
Left. Yeah, right. Thank you.
Big audience.
Am I right that in terms of CAP theorem, you did lost consistency?
No.
Why not?
Well, it's an eventually consistent system.
Eventual consistency.
Yeah,
but
exactly.
It's not,
so,
yes.
and that's obviously where we have to compromise on. But like with a 5-node cluster, you're essentially protected against the failure of 2 nodes, which does the job.
Okay, and I have another question. Could you please go back to the picture, to the schema with Kafka and consumers and producer? And could you please describe in details how do you commit your message to Kafka? No, the last one.
This one?
Yes, yes, this one, yes. So payment processor sends one message during his job, right? And another message, commit message, right?
No. So what the payment processor is doing is is this thing, right? So the payment processor essentially just is, let's go back. It's just saving the message, the result to the database. And then what we're doing is we're just taking it and sending it out to Kafka. and removing this message from the database. So for each transaction that we complete in the system, we store a local entry somewhere in our database, essentially saying this has been finished. This is the unique ID of this action, and then we're going to forward this whole thing to Kafka.
Я напоминаю, что Harald продолжит еще в дискуссионной зоне в течение 1,5 часов. Еще я напоминаю, что те, у кого красные полосочки на бейджах, могут, кстати, идти обедать. Если вдруг вы не хотите задать вопрос или послушать ответы, у нас, я вижу, тут уже несколько вопросов. Дима, у тебя в том крыле есть вопросы? Просто я забрал микрофон, и там, видимо, все спокойно.
Нет, кажется, здесь нет.
Thank you very much, Harald, for your report. I'm here again. As far as I understand, you use Kafka as a transfer layer. Have you ever thought about building this solution on a messaging framework like Akka or Vertex?
It's a very good question. No, we didn't. But it's actually one thing that you could use to modify this whole thing. But still, you need a transactional way to get the data onto the next node. That's the main point of it. But yeah, it's a very good question actually.
Several questions here. First, have you considered using just regular HDDs against the SSDs? And how long is your retention time?
So retention time is 7 days in our system. More than enough for us. I think whether it's an HDD or an SSD doesn't matter much because anyway we're using the page cache to do the actual write and then the system syncs it back. So I don't think that there will be a big difference, to be honest.
Yeah. Second one, how do you what if the exception occurs during the processing? Do you where do you put the messages, like separate failed messages queue, or do you resume the processing, or everything stalls?
Everything actually. So some of the teams that are dealing with this, they do some kind of replay thing. So so there's a possibility to replay the message, or we just just fail fast and try to rerun the message. It really depends on the use case. But we have both. We have failure queues. We have republishing of messages. We have just like skipping them, all sorts of things that we're doing.
Right. Last one. Have you ever encountered producer duplicates?
Sorry?
Producer duplicates.
Like sending out messages twice?
Yep.
Yeah, I think. Well, I can't tell you exactly, but it's more than likely that we had.
Hi, thanks a lot for the report. I have one question. Do you create some mechanism for rollback first part of transaction if second part was invalid or crashed by some reason?
No, because you can't. The assumption behind all of this is like that once we complete the first transaction, the system is in a valid state. So we always, if the second one crashes, we have to fix what's broken in the second one and just redo it again. But you would never, there's no reason to roll back the first one. What you would instead of doing, essentially our system works like a big state machine. So let's say for some reason the second transaction crashes, then we would move the whole system to, let's say, a payout gets rejected, which is something like maybe what you're saying. Then we would move the whole system to a cancel state or whatsoever. But transactions, local transactions, if they are done, the system is in a valid state. There's no reason to roll it back.
I got 2 questions about the deduplication part.
Yeah.
First of all, do I get it right that you are just using a SQL database to store all the processed messages?
Yeah.
Then your table should be growing very fast and the index should be decaying. And the second question is, how often do you need deduplication actually? Is it something that just happens naturally or during something like service restart?
So on the first one, very good question. I actually forgot to mention this. So our incoming message table, what you call it, has a retention period as well. It's actually the same as the Kafka broker. has the topic. So like we're deleting messages after 7 days because they can't come in anymore because, I mean, the Kafka topic has a retention period. And with 7 days of messages, which can be actually grow up to like quite a bit. It's still like if you do this, because you're doing the lookup, the deduplication on a primary key, it's still super fast. It actually doesn't degrade a lot. And I'm not sure I fully understood the second question. So yes, we're doing deduplication all the time. It's just like part of the surrounding framework that we're using to consume the messages.
How many of them should be deduplicated? What percent?
So the question is, what percentage of messages are we actually deduplicating, if I got it right? I can't tell you the number, but I would say it's in the it's less than 1%. But sometimes, well, what we've seen, what happened actually is because the way Kafka works is if one of the nodes loses a consumer offset, it will be reset, and then what we've seen is that the whole topic has been replayed to the service, and boom, then you need, then you obviously, but this happens very rarely.
So we've got, I guess, one more question. I see.
Thank you for the talk. You said, if I got it right, that with GTL we can have an out of memory if the consumers are too slow. What's the difference with Kafka if the consumers are also slow?
Well, because the consumer, and we can go back to this. We can go back to this picture. Where do I have it? This one. Sorry, this one. So the consumer just there's this essentially there's just this piece of this big array is on the Kafka broker, and the consumer essentially maintains the index. Its position in this array on the consumer side. So the broker doesn't know where the consumer is. And this way, each consumer can advance through this array as fast as possible until it reaches the last index. And that's why you can, as you can see it here, like even if a consumer 2 would be still at offset 1, consumer 1 could already be at offset 10. They wouldn't slow it down each other. And it's no longer a memory issue because you don't have to keep the state in memory and to push it out on, to the consumer essentially. That's what makes Kafka. This is actually the very smart thing, and that's why I like Kafka, because it's like you don't. It's just all the state is kept on the client. Services can't break each other, and this just scales essentially.
Thank you.
Yeah.
And I guess we are done. And thank you again, guys. Thank you.